Greetings. Welcome to week 6 of CS320 Advanced Optical Internet Programming. Uh, this is a recording just in case Dr. Donqua chooses to use this as a method. He will be taking my place in my stead for week 6. So basically, this is a recording that kind of gives you the highlights of what we're going to be doing in week 6. And to start out, let's talk about the learning objectives. What are we trying to accomplish in week 6? Okay, we want to explain Java's concurrency model. Okay. Describe thread lifecycle. When we start a thread, what does that mean? What are the steps it goes through? What can we do? What cannot we do? Or what we can't do? Create and manage threads in Java. How do we do those managing of those threads? Applying synchronization and thread safety techniques. Design thread-safe object-oriented systems, apply behavioral design patterns in concurrent systems, reason about common concurrency hazards, and introduce asynchronous programming concept. Uh, you know, just to boil it down, we're looking at how do we run tasks, either concurrently or in parallel. Okay, so that's the basic crux of what we're going to be doing here in week 6. As far as the positioning of the course, it builds on the behavior patterns we talked about in week 5, exception handling and subsystem boundaries in week 4, and functional pipelines and a couple of design in week 3. Expectation, if this is going to prepare you for concurrent collections and executors. Again, key thing here is concurrent, reactive and event-driven architectures, and enterprise and server-side Java development. Finally, project scalability. We have already talked about scalability and what that buys us and why we need it. So looking at just kind of the overall of what we'll be doing in week 6, starting out, here are the things that we're going to be kind of concentrating on. Next, let's talk about our definitions of the main terms we're going to have in this class. Okay, here are the key terms that we're going to be addressing in it this week. We have concurrent programming, writing programs that allow multiple tasks to run during the same time period. Asynchronous programming style where tasks run independently without blocking the main program. So we have our main program, but we kick off another task that basically is running at the same time, but independent of the main processing of the main program. Parallel execution, running multiple tasks at the same time, using multiple processors or multiple cores. Multiple threads, using several threads of execution within the program to basically handle different tasks so they can run simultaneously. Now, note that this could be a task for two separate jobs, or it could be a task where we're looking at one program. We have 3 pieces to it, so we put each one of those 3 pieces on a thread, and we let those basically run independently. Concurrency bugs, errors that occur when you got multiple threads interacting incorrectly. What are some of the things that can happen and why they happen? Race conditions is a bug where multiple threads access shared data at the same time, causing unpredictable results. Race conditions, deadlocks. We have talked about this briefly starting in the class, but deadlocks is a situation where 2 or more threads wait on each other forever, preventing the program from continuing. By virtue of deadlock, we can't do anything because one program is waiting on another program at the same time that they're waiting on each other. Inconsistent behavior, unpredictable results caused by threads interfering with each other. Core thread model, the basic system Java uses to create, manage, and schedule threads. Thread lifecycle, the stages a thread goes through, such as creation, running, waiting, terminating. We'll be talking about that. Coordination, managing threads of managing how threads communicate and work together safely. What are the things we have to put in place? Thread safety, ensure that the shared data remains correct when accessed by multiple threads. Asynchronous programming concepts, techniques that allow programs to perform tasks without waiting for each other to finish before starting another task. Concurrent execution, multiple task processing during overlapping time periods. Parallel execution, task running simultaneously on multiple cores. Thread, smallest unit of an execution within a program. Runnable is a Java interface used to define code that can run in a thread. Or runnable basically saying I can kick this off independently. Okay, is another definition for runnable. Synchronized blocks, code sections that allow only one thread at a time to access our shared resources. Here's an example. We'll be doing a deep dive into this shortly. Atomicity, ensure that all operations complete fully without interruptions from other threads. They're independent. Shared mutable state, data that multiple threads can change at the same time. Definition of mutable versus unmutable. Thread confined, data that is accessed only by only one thread, preventing concurrency problems. Decouple concurrent components, designing systems so different concurrent tasks can operate independently. Non-blocking execution, running tasks without forcing other parts of the program to wait. And trial and error, attempting to fix concurrent problems by guessing instead of using proper design. So if you see basically the crux we're going is parallel processing, and how do we structure our programs or our systems so that we can basically run multiple tasks at the same time and not cause conflict in running those tasks at the same time. That's the crux of what we're talking about in week 6. Okay, now let's take a look at the homework assignment that we'll be having for week 6. And here it is. We have multiple parts. Part 1, concurrency concept analysis. I want you to answer these following questions. Explain the difference between concurrent and parallel execution. Describe Java thread life cycle stages. Explain why raw thread usage can be inferior to task-based approaches. Define what a race condition is, atomicity and visibility. Explain why immutability, improves thread safety. Basically not being able to change things. In part 2, code analysis, here's some code that we're basically given to you as far as sharing a counter. Okay, want to answer the questions, identify the concurrency hazards, what can go wrong, explain why count plus plus is not atomic, refactor safety using synchronized or atomic integer. Remember refactoring, it says I'm rewriting the code in order to make it more efficient, but I'm not changing the purpose of what the code is doing. That's refactoring. I'm rebuilding it. Okay, so that's what we're being here. How do I refactor safely using synchronization or atomic integer? Explain the trade-offs of both solutions that we have here. In part 3, we have thread safe design refactor. What we want to do is given an inheritance heavy design, where we basically are here. We're going to create an abstract class that we're going to execute. And what I want you to do here is refactor this using strategy patterns for execution behavior, command pattern to encapsulate task requests, and observe pattern to notify completion. So taking that, we want to basically enhance that processing to include this functionality and explain how patterns reduce contention. Part 4, concurrency design narrative. Okay, students must identify shared and thread confined objects, explain locking strategies, and discuss deadlock risk. and justify synchronization decisions. Okay, so that's our homework assignment, okay, that we are basically looking at, okay. Next, we'll look at the project assignment and what we're going to be doing with that for week 6. Okay, talking about the lab assignment, what the expectations are for week 6. We have this lab scenario. We're designing a multi-threaded order processing system. This system can have multiple clients submitting orders. Orders are processed concurrently. Inventory must remain consistent, and observers are notified when orders are complete. So that's the functionality we're going to be looking at for this particular project lab for week 6. Lab requirements: number 1, thread creation. Implement using thread plus runnable, and explain why executive service would be preferable in this particular case for this particular scenario. Share resources, inventory, must protect shared inventory count, prevent race conditions, demonstrate incorrect behavior without synchronization, and then fix it. You can either use synchronized or reentrant lock. As I said, if there's some particular thing that's in the homework, standard practice, you need a little bit of additional information, go through that research project and looking up these terms, seeing what they do, seeing how they fit in. Again, if you, for some reason, can't get it or doesn't understand, then hey, get with me and we'll work through it. Okay. But again, this is the things that we would have covered in our lecture. Behavior patterns in concurrency, apply 1 in this process that we're building, whether it's observer, command, strategy, or state. Notify on order completion, encapsulate order requests, the command, strategy, dynamic processing algorithm, state, order lifecycle transitions, and explains how this reduces coupling. Deadlock demonstration. Here, we want to intentionally create a simple deadlock scenario, doing this on purpose. Then factor to eliminate it. Students must explain why the deadlock occurred and how they need to fix it. Asynchronous extension. So this is a bonus. We're going to bypass that. We don't have any graduate students. Again, as usual, I'm not going to have you to be having this. You can run it as a bonus. I will take that. But just go through the 4 requirements that we've gone over for the lab requirements. Don't worry about 5. Okay. That won't be part of the grading process. Okay. So that's basically what we're looking at for week 6 as far as the project is concerned. Let me know if we have any issues. So right now we're going to do deep dive into the lecture itself that I will be presenting next. Okay, so let's move on into the to the lecture that is associated for week 6. Okay, so what we see here now, I'm going to real quickly jump down to a next page and kind of get the definition of concurrency. These were defined in the definition section that we did previously, but just kind of reemphasize, what is concurrency? Concurrent programming. Concurrency means multiple tasks progress during the same time period. These tasks may share system resources. They may interact with each other. They may run on different threads or different pathways. Okay, so that's basically what we're doing. Going back to this question, why do we need to do that? Why do we need to have concurrency? And you look at some of the things that are happening in various systems. We have web services handling many users. We have games updating multiple systems simultaneously. We have databases processing many queries, cloud services for thousands of requests. So in this case, we're going to need modern software is going to have to be able to handle multiple tasks at once. We cannot live in an environment that everything is single threaded. Okay, don't have the time. So to do this, programs uses threads. We'll do a deep dive into that, and then concurrent execution. Okay, first, share system resources. Multiple tasks use the same data resource. That is uh, basically one of the things we're going to be worried about, or not worried about, but the things we're going to have to consider that when we're sharing resources, how does concurrency and parallelism, how do they work? So here's an example. This is taking the counter here. Okay, and basically this is being shared, but all we're doing is incrementing the counter by 1 when we call it. So here's a particular uh, program. Here's the main. We're creating a new counter, okay, from the class. Here we're making a runnable. The runnable task is basically saying that I can run this task multiple times, okay, in different situations. I can use this to not have to be single threaded. When I say runnable task, I'm creating the ability to run this task separately by many sources. Okay, so that's what the runnable is doing here. So this is saying that I might have one person calling it, I might have 20 persons calling it, but again, all of them are going to be running at the same time. And the way they're going to be doing that is here by when we're creating a thread. Okay, we're creating a thread and we're saying start that thread, okay, which is going to be executing, okay, this processing. So here I'm starting 2 threads to do the counter, running simultaneously. 2 threads share and update the same counter, but with that, you can cause errors without synchronization. If I don't synchronize, I'm going to run into issues. We'll talk about that. Okay, interacting with each other, task, communicate, or coordinate. Example, here's a particular situation where I have a message. A message is put into a mailbox. I have a receiver that gets that information from the mailbox. Yeah. So I have to synchronize this. I have a situation where I don't want to go to the mailbox if I know there's nothing there, or if I go to the mailbox and there is nothing there, or I'm sending stuff to the mailbox. Okay. I thought I had sent it, but I didn't send it in coordination with the receiver. So here is kind of an explanation of this particular situation. Okay, where we're taking something, there's no message there. Okay, we synchronize. We look at. We says, "While we have a message, try wait exception." So we say we're going to wait for a message. Okay, and when the message comes in, when message becomes true, when I send it, I'm going to notify. Okay. So this particular part is sending a message to the receiver that's saying, hey, I just sent you a message. And I have to synchronize this here with the receiving. Okay, so here's the sending. I'm sending the message. Okay, here's the receiving where I'm receiving the message. Okay, so this says go ahead and get the message. And after I get it, I'm going to set a notification that says, okay, there is no other message because I already received it. That's what's being done here. So I received the message. I'm now setting off the counter that says, okay, I received it. So my state of being, I'm going to notify my sender that, okay, I'm ready for the next message. That's what's being here. So this is the receiving side. This is the sending side. Okay, one thread sends a message, the other receives a message. They coordinate using wait and notify. Okay. They coordinate using wait and notify. So here we have the notify. Here we have the wait. Okay, so what are we waiting for? Okay, when I'm doing a send, I'm waiting for a notification that says I don't have a message. Okay, so I need to send one. Okay, so I'm waiting for that. Once I get that indication that hey, somebody wants a message, then I'll send it. I'll notify that that the message has been sent. The receiver is waiting for the message to get there. Okay. So you're waiting, we're waiting here. Okay. Once we get the message, okay, we'll set it to says, okay, now we're in a state where we need a new message, and I'm notifying you of that. Okay. Okay. So that's what we're basing. This is one of the interaction models that we're going to be looking at that you can run into that we need to discern, when things can go wrong. Okay, so one thread sends, one sends, one receives, and they coordinate using the wait and notify. Okay, we're going to delve into this a little bit more later. Okay, and then we're running on different threads. Okay, tasks execute at the same time independently. Okay, here's an example. Here we're creating thread 1. Okay, in this particular case, we're not doing anything elaborate. We're printing out task 1 is running. And then we're going to start thread 2. So here's thread 1, here's thread 2, and we start both threads. The key thing here, 2 tasks running concurrently on separate threads may execute in any order. So your normal thinking that T1.start, then T2.start, then T1 would run before T2. Not necessarily. It may, but it may not. There's no guarantee that the 2 threads are going to be running in the order that I started them. So that's the problem. If I'm building and starting threads, assuming that they're going to be running in the sequence that they're running into the sequence that I started them, then I might be in trouble if T2 starts before T1. So I have to control this. These are 2 running tasks concurrently on separate threads, may execute in any order, and with that, I may get total results that I have no idea how I got them. So quick summary, okay, share resources, same data, risk of conflict, interact, tasks communicate with each other, different threads, okay, tasks run at the same time. Those are 3 situations from concurrency and parallelism that we're going to need to make sure that we're able to fix. Okay, so let's talk about parallelism. Parallel execution occurs when multiple tasks run at the exact same time on different cores. Now, again, keep in mind that parallelism and concurrency are 2 different things. Okay, and which is one of your assignment questions. How are they different? Okay. But this is a case that when I am running in parallel, I am running at the exact same time in the same time period. Here's just an example here of I have a CPU, and I'm basically here's my core. So I have multiple tasks that I'm running, okay, at the same time. A CPU core is like an independent worker inside your computer's processor. Each core can execute instructions on its own. Okay. Think of it as having each core being a separate computer, okay, to keep it simple. So that's what we're doing here. We can have a single core, okay, and we can have multi-core. Single core CPUs, 1 task at a time, very fast switching with still 1 worker. I work on task 1, task 2, task 3, task 4, and I'm flipping back and forth with each other. So I'm not, there is some savings here. I'm not running a program to completion before I start the next program. What it's saying is from a single core, I'm going to process part of program 1, then I'm going to switch to program 2, then I'm going to switch to program 3, and I'm going to run pieces, okay? And then I'm going to go back to 1. So I'm running pieces off the single core, but they're single threaded. 1 task at a time, very fast switching, but still 1 worker. When I'm talking about multiple cores, multiple tasks at the same time, I have multiple workers, okay? I have 4 workers, okay? In this particular case, then each one of those workers can be doing something differently at the same time in the same time period, okay? So how parallel tasks work? When a program is designed for concurrency, each task thread can be assigned to a different core. So if I started before we had the two tasks, task one, task two, we started two threads. I could put one task on one core, one task on another core, and now I'm running these at the same time. Okay, run those tasks simultaneously, and they are called parallel processing. Here's a simple example. Imagine you have one core, one student doing homework. Four cores, you have four students doing different assignments at the same time in that same time period. The result, work gets done faster when the cores are split correctly. Okay, important. Okay, more cores, more ability to run tasks in parallel. Not all programs use multiple cores automatically. Developers must design programs, their threads, to take advantage of cores. So it's something you have to build into your design process to say, I want to take these four threads and I want to spread them over these four cores and can basically do them at the same time. Too many threads can cause overhead instead of speed gains. If I have, 1,000 threads, yeah, okay, the time that's going to take me to coordinate those threads across multiple cores may be to my disadvantage, to where I'm not getting the results that I want to get to. I'm not getting those speed gains. Again, keep in mind that even though we're working on multiple cores, okay, you can't make the assumption that they're basically standalone. They still could be accessing resources that are shared. Okay, that still could be the case. So whenever we run cores in parallel, we have to still look at the design to make sure that the three items we talked up here. Okay, so as far as here sharing resources, okay, interacting with each other, or the fact that threads don't run in the exact sequence that we think they may or should have based on when we started the threads. Okay, so we still have these issues, even though we may be running on separate cores. Okay, so looking at a summary, CPU cores enable true parallel processing, allowing multiple threads to run at the same time. Concurrent versus parallel. The concept of meeting concurrent, task running, task overlapping in time. Okay, I'm running multiple tasks in the same time period, but not in parallel. Okay. I do one, I do two, I go back to one, I do three, I go back to one, I do four. I'm doing multiple tasks during the same time period, but they may not be in parallel. That's for concurrency. In parallel, tasks run simultaneously. I have four tasks. I'm running one, two, three, and four all at the same time. Okay, so that's the basic difference between concurrency and parallel. Concurrency can exist even on a single CPU through scheduling. Okay. Now, I scheduled, task one, it runs for 20 seconds. The next thing I schedule is task five. So I can basically schedule the tasks that are running in a certain time period, which is basically the concurrency that I'm basically using for this. Okay, threads. A thread is the smallest unit of execution within a program. Programs often use multiple threads. Okay, I can have a thread for the main application processing, another background worker thread that I could be using. I can have a network request threads. So I can have any number of threads that I might want to use and basically use those to run either concurrently or in parallel. Okay, one way you can think about it, a program is a whole application. Think of a Microsoft Word. A process is a running instance of that Microsoft Word. A thread is a single task inside that running program. So inside the Microsoft Word, what I'm doing, the thread is a single task that I'm executing. Okay. So that's what we're looking at. That's why we're saying the thread is the smallest unit. So because we're breaking up the various tasks that we need to do, okay, into several simple actions versus running the whole program. I can break up that program into ever how many pieces I want to break it up into, 2, 10, 20, 100, and basically take those threads, make them runnable, which says, okay, I can run these at the same time in parallel. Okay, everyday analogy, imagine you have a restaurant. Okay, the program is the restaurant. The process is the restaurant is opening and operating. The threads are individual. I can have one person cooking, one person taking order, one person serving food. Each one of those is a task. Okay, I can put those on separate threads. So they're not basically interfering with each other. Okay. Now, but one thing I also can do is I can basically do those in parallel. Okay, I can cook at the same time I'm taking an order. I have a chef doing the cooking, and I have a person basically looking at and taking orders and serving food. Okay, each worker thread is doing a specific task, but all belong to the same program, and that's the restaurant. So that's kind of an overview of how you might be looking at things. Okay, from a simple code perspective, here I'm creating a new thread, uh, T1, and here all it's going to do is, printing document. Okay, this thread is one unit of execution doing one job. We talked about runnable. Okay, runnable Java creates threads using runnable interface. That is the Java utility. Runnable says, okay, I want to create multiple uh, runnable tasks that can be run at the same time. So that's how we're defining runnable for the task. And then we're inheriting. Okay. So we basically inherit or extend runnable for the task we're creating. So here we're creating a new thread. We're starting it. Runnable defines what work the thread performs. Okay. So runnable and thread are connected to each other. Runnable is the class. Thread is basically the subclass. Okay, so what are the thread life cycles? Okay, I created a thread. It can run in parallel. Okay, what are the steps that we'll be going through? Okay, threads move through several stages. Okay, typically a thread first will be new. I create a thread. Runnable, I'm ready to execute. Okay, I can start that task to actually start running. Wait and block, pause for resources. I need a resources, I'm waiting to get that resource, or I'm blocked from getting that resource. This is one of the main reasons, okay, when we talk about why a particular thread may not run in sequence. I can start thread one, start thread two. My expectation is one will run for two, but I start thread one, it gets stopped. It's waiting or blocked for something. So thread two goes ahead and execute. Then we come back to thread one. So because we have this waiting or blocked instance that can happen when we're running, this is where we're getting basically caught in the fact that a particular thread may not run in sequence. Okay, so we have new, runnable, running, waiting or blocked, and then terminated. Okay, the thread is finished. Okay, understanding these cycles helps develops reason about thread coordination and scheduling. Okay, concurrent problems. When threads interact incorrectly, results are unpredictable. We have bugs. Uh, okay, concurrency bugs. Okay, so here's what happened when we're having concurrency, when we're running concurrency. Race conditions. A race condition occurs when multiple threads modify shared data at the same time. Example we've been giving is the counter plus plus is an example of that. Two threads update a bank account balance simultaneously. If we don't have a coordination, what's actually in your account could be incorrect. If I'm having uh, two threads updating that bank account at the same time. Deadlocks occur when threads wait on each other forever. Right here, I have a thread A, it's waiting on thread B, and I look at thread B and it's waiting on thread A. Okay. Okay, both are stuck and we're in a permanent lock situation. Okay, inconsistent behavior, concurrency bugs cause random failures, unpredictable output, and hard to reproduce problems. That is the key thing with threads and parallelism and concurrency when updating resources is you can't duplicate it. Okay, based on the timing and what resources are being asked for and what resources are available, it's very hard, if not impossible, to get that exact same scenario so that you may be fix it maybe by scheduling, because you can't you can't redo uh, the environment, the situation, because of the randomness of what's happening. So that's where the hard to produce problems comes in. I can't guarantee that things are going to run in the order that I think they should. Okay, these are bugs often difficult to debug. Okay, we have thread safety. Thread safety ensures that shared data remains correct when accessed by multiple threads. That is a design issue. Shared mutable state. Problems occur when multiple threads modify the same data. We talked about that. Counter plus plus. Atomicity. Atomic operations complete fully without interruption. Okay, that we can control. We can control this says, okay, this particular task has to complete in its entirety before someone else gets control. Okay, this prevents partial updates from multiple threads. Synchronized blocks. Java provides synchronization to protect shared data. For example, here I'm doing a synchronized lock, and it says that once I'm in here updating counter, nobody else can update counter. Okay, I am locking it. So that we won't have the position where we have two tasks updating a resource at the same time. Only one thread can execute in this block of time. Okay, so safer concurrency design. Good concurrency design tries to reduce shared data. Thread confined data. Data is used only by one thread. No synchronization needed. That is one of our design goals we might be trying to get to. Decoupling concurrent components. Design components of threads operate independently. This reduces contention and complexity. Non-blocking execution. Non-blocking allows the task to continue running without waiting for other tasks to finish. Okay, we do not block each other. And again, looking at these, all of these are designs. Okay, when you're running and creating your Java program, you're looking at, especially in the case when you're doing threads and runnables and that sort of thing, what happens when I have two tasks or two requests happening at the same time? Each one on a different thread. Where can I get into trouble? Where can I get problems? Where can I get into trouble? And design to prevent those from happening. Okay, that's what we're basically looking at in as far as concurrency and parallelism. Okay, so the non-blocking execution. Okay, final thinking, a common mistake developers make with concurrency is a trial and error debugging. As we said, since we can't totally duplicate the situation exactly, trial and error is probably, if you get it, you're lucky. Okay, that you actually fix something. It is not a stable way of determining where my problem is. Instead of guessing, fixers developers must reason, share state, thread coordination, synchronization, system architecture. Currency requires careful design thinking. It has to be affirmative. It has to be a process that we actually put effort into, and it's not going to happen by itself. So, a final summary, we talked about concurrent programming, parallel execution, threads, and runnable threads lifecycle, race conditions, thread safety, atomic operations, synchronization blocks, shared movable state, and non-blocking execution. Okay, these are basically the tools that we have, okay, in order to prevent problems from happening, but still allow that very important process of running things concurrent and in parallel to basically speed things up. Okay, we still want to have that capability. We just have to do a little more thinking on how we do it. So modern software relies heavily on concurrent design. Understanding these concepts is essential for building scalable and reliable systems. Scalable. Yeah, I have to have concurrency. If I go from five uh, people, five individuals executing a particular program, and I go from 5 to 1,000, the way I handle that scalability up is that I basically start using threads. I start using cores. I start running a task in parallel, so that even though I have 1,000, I can run 500 of those in parallel. Okay, so that's where the concept comes in and what we're looking for, what we're reviewing here in week 6. Okay, so closing question: why are concurrency bugs often harder to detect than normal programming bugs? Okay, we went over these. Your timing differences, your thread interactions are unpredictable. Your bugs may appear randomly, and it's difficult to reproduce consistency. One of the bad things about parallel and concurrent processing. Okay, so that's what we have. This is the recording for week 6. Just kind of an FYI, week 7, we are basically taking that time to use uh, the project and developing our overall project. Again, taking what we did in each week from week 1 to week 6, putting that into a concise presentation for advanced object-oriented programming. That would be for week 7. But have a good week for week 6, and let me know if you have any issues at all. Have a good one. Bye.